Today is the last formal lecture, but I'll see you guys tomorrow also. So tomorrow we have 2 example classes, 11 to 12. All of you are welcome to that class. 11 to 12 in ATB 207 and 4 to 5 in the same room, ATB 207. Okay? Now, some of you have given me questions to do, so I'm going to start with this exam question 2014-15 question 4, which is this one here, right? All right. Yeah. So you have right? So you have 2 independent random samples. The first random sample is from the normal distribution with these parameters. The second random sample is from an exponential distribution with this parameter. Now the first part is to write down the likelihood function. Remember what I told you. When you have 2 independent random samples, the likelihood function is the product of the product, right? So what I mean by that is the following. What you do is you write down the likelihood for the first sample, which is all right, this is the likelihood for the first sample, and then you write down the likelihood for the second sample, which is, you know, the PDF of the exponential distribution, right, which is 1 over sigma squared times E of and then you take the product of the 2. So that's what I meant when I say product of products, right? It's the product. This is the likelihood for the first sample, the likelihood for the second sample, and the product of the 2, right? Is the likelihood, right? Now you simplify this, guys, you will get all right, this is the simplified form of this, and you can simplify this further. Let's simplify further. Okay, you can have this is sigma squared. Right, this is the most simple form you can get to. All right, the next step, as you all know, is to take the log of the likelihood function. So the log of this, so it will be minus n by 2 log of 2 pi minus 3n log of sigma and minus 2
exponential distribution should have eaten y.
Oh, sorry. Thank you. I'm in a different world now. Sorry. Thank you for pointing that out. All right, there should be y here, not x. Thank you. Right. Okay, so this is the log of the likelihood function. Now, because we have two parameters, we need to do partial derivatives of the log likelihood with respect to the two parameters. So that's what I'm going to do next. So let me put this over here, guys. So the first thing is I'm going to take the partial derivative with respect to mu. Yeah, and that will be equal to that will be equal to this, and you can simplify this further to yeah, and if you set this to 0 and solve for mu, you will get mu hat equal to this, which is the sample mean, of course, right? So the MLE for mu is the sample mean. Now, similarly, I'm going to differentiate the partial derivative with respect to sigma, right? So you differentiate this with respect to sigma, you get this, and the derivative of this with respect to sigma is going to be plus yeah, all right, and you set this to 0 and solve for sigma, or sigma squared in this case. It's easier. So it is sigma squared hat will be equal to 1 divided by 3n okay. So I replaced mu by mu hat. Of course, we already found the MLE for mu, so we can replace. In the next line, we can say that this is equal to all right, so this is the MLE for sigma squared, and this is the MLE for mu, right? And that's it. I guess the remaining two parts of the questions are to find the bias and the MSC for mu, and the bias and the MSC for sigma squared. I assume you can do that, right? Yeah. So I'm not going to do that. So that's one question I got today. The second question I have today is from a different exam paper. Let me find out. Unless you have some other questions you want me to do in the meantime. 13, 14. Yeah. 3-1. is this one here. This is from 2012-13 exam paper. This is exam all right, guys. I'm going to do only part B, because part A is just bookwork, right? Part A is just bookwork question. Part B, you have two variables, x and y, uncorrelated. X has mean 2 theta and variance 4. Y has mean theta and variance 2. The parameter theta is unknown. Right, now let's do part 1. You're told that theta 1 hat is equal to x divided by 4 plus y divided by 2. And theta 2 hat is equal to x minus y. So these are two possible estimators of theta, right? And the question is to find the bias in the MSC. I mean, these are questions we have already done. We have done questions like this in the past, right? So to find the bias of theta 1 hat, all you have to do is just use the definition. This is the definition of bias. So this is the expectation of x by 4, y by 2 minus theta. So this is 1 over 4 times the expectation of x, 1 over 2 times the expectation of y minus theta. Now we are told that x has mean 2 theta, so it's quarter times 2 theta plus a half times theta minus theta, and this is of course 0. So the bias theta 1 hat is an unbiased estimator, right? And similarly, to find the bias of theta 2 hat, you do the same things, the same kind of stuff, right? Yes? So this is expectation of x minus the expectation of y minus theta. The expectation of x is, you're told, is 2 theta minus theta, which is 0. Right, so both estimators are unbiased. So that this implies that theta 1 hat and theta 2 hat are both unbiased, right? Now, to check for consistency, you need to find the MSC. Now, since the estimators are unbiased, MSC is the same as the variance, right? So that's what I'm going to do now. To find the So the first, I'm going to find the variance of theta 1 hat, which is the variance of x by 4 plus y by 2, which is 1/16 times the variance of x plus one times the variance of y. Yeah. Now, if you look at the question, guys, it says that the variance of x is 4, and the variance of y is 2. So if you do this, you get a quarter times a half, which is equal to 3 over 4. Okay, is that right? So the variance of theta 1 hat is 3 over 4. And similarly, the variance of theta 2 hat is the variance of x minus y, which is the variance of x plus the variance of y. right, because of independence. Remember, I've used independence to get from this to this and this to this, right? Variance of x is 4 plus 2, which is 6. All right, so obviously, this implies that the variance of theta 1 hat is less than the variance of theta 2 hat, and therefore we prefer so we should prefer the theta 1 hat to theta 2 hat. Okay. So this question is not. Can you do the last part, sir? Hello. What about the last part of? You can do that. Okay. So I'll leave it here. And the next question I got is 3.1. It's the same exam paper. Part 1 of question 3, same exam. Can I take this away, guys? Yeah? Okay. So this is the same exam paper, that is exam 2013, 2014, question 3, part 1. Okay. Okay. Now you're told that you have x1, x2, x3, x4. They're all IID uniform variables on the interval from 0 to theta. And you're told that the only thing that you observe is the min of x1, comma x2, comma x3, comma x4. And the first part is asking you to find the CDF, or the cumulative distribution function of y. Yeah? Y is this. So, I mean, I've done, to find the CDF of y, which is by definition is the probability that y is less than or equal to this. Yeah? In the case of minimum, it's always helpful to use at this step, right? At this step, it's always a good idea to use the complement rule and write this as 1 minus the probability that y is greater than y. And the reason for that is, I'll give you in a minute. The reason for this is that if the minimum is greater than a number y, then each element in the minimum has to be greater. And you cannot say the same thing with when you have the less than sign. You follow what I'm saying? Yeah? If the minimum is greater, then each element has to be greater. But it doesn't apply here, though, that if the minimum is less than something, it doesn't mean that each element is less than. You follow what I'm saying? So it's important, therefore, that you write this in this form, right, before you proceed. Okay, so this implies that x1 is greater than y, x2 is greater than y, x3 is greater than y, and x4 is greater than y. Right, now because of independence of x1 to x4, you can write this as the product of the probabilities right? All right, I mean, each probability is the same, so this is basically 1 minus the probability x greater than y to the power 4. Okay, because x1 to x4 are IID, all right? Now this you can write as 1 minus the probability that x is less than or equal to y to the power 4. Now we know that x is uniform on the interval 0 to theta, so this guy here must be do you see where this comes from? It comes from the lecture notes, guys, that this is the CDF of the uniform distribution at y, which is, if you look at the lecture notes on page, I can't remember the page number, but if you look at the lecture notes, you will see that this is equal to this, right? Okay? So the answer is 1 minus, so this is the CDF of what? Okay? And the rest of the question is not difficult. You should be able to do the rest. All right, guys. Any other questions, guys? Yes, you have one? No? Come on, guys. You have. Don't wait till the last minute to revise for this course. This course is something you should start revising from the first date, because there's so much. I have put so much material online. Especially support material. You cannot possibly go through all the material I have put online in the last couple of days. So it's important that you do that in a gradual fashion, not till the last minute. Sorry? Booklet, you mean? You mean this 40? You mean this one?
Yeah, I was just wondering how to get find tau.
Well, once you find the MLE for lambda,
Yeah.
then the MLE for tau is just 2 lambda hat minus 1 squared. Yeah. Is that your question, sir? Okay. I thought this is one of the examples I did in the tutorials, I think. Yeah. Yeah. Was in a problem sheet. Any other questions, guys? Yes? What about you guys over there? You have any questions, sir? No? Anyway, earlier somebody asked me about the 2008-9. This is the paper that's without the solution. Unfortunately, I lost the solution. I'm gonna do. One of you guys asked me to do one of the problems here. It's this one, okay? So let me do this one now. Where's my pen? So this is the exam paper without the solution, guys. Exam 2008, 2009, question 5, part B. Okay? So I'm going to do this part, guys. So let's look at part 1, for instance. The other parts are similar. So you have this hypothesis, and the question is to find the power function. Right? Remember, the definition of power function is that you reject, is the probability that you reject the null hypothesis when the value that you're given is sigma. So it's very, very important that this sigma is arbitrary, right? It doesn't take any specific value. Sigma is not a fixed number. It can be take any value, right? Right. And the first thing you must realize, in this case, what is the rejection rule in this case? You should look at the lecture notes, guys. If you look in the lecture notes, you will see for this hypothesis that sigma equal to this versus not equal to, these are the rejection rules, right? So the rejection rules are that n minus 1 s squared divided by sigma 0 squared is greater than this, or yeah, the same thing, right? So this is by equation 1, 1, 2, 1, 1, 3, right? I mean, you don't need to remember these equations for the exam, by the way. There are only 3 rejection rules that you need to remember for the exam on the 23rd of May. And the 3 rejection rules are in the formula sheet that I put online. Yeah? The other rejection rules, all these ones, you don't need to know. But anyway, I will do this. I mean, I'm not going to stop doing just because. All right, now, because these 2 events are mutually exclusive, that is, they cannot occur together, right? You can write this as the sum right? So that's using the fact that the 2 events, that is, this event and this event cannot occur together. That is, meaning they are mutually exclusive. So therefore, the probability is the sum of the probabilities, right? All right. The next thing I'm going to do is that the next thing you must realize is that the sigma 0 squared you are dividing here and here are not the true population standard deviation. The true population standard deviation is sigma. It's these 2. So the next thing you must do is to replace the sigma 0 by the true population standard deviation. Right, so that's what I'm going to do. So I'm going to replace sigma 0 by sigma squared. So I need to multiply by the same thing and keep it. Okay, right. And the next thing I'm going to do is I'm going to take this factor here and this factor here to the right hand side. Yes. So it will become right. All right, now this is the decision time. All right, now can you tell me like what distribution this has? This one and this one. What distribution they have and why? You must know this by now. Chi-squared, yeah. It's because, guys, remember what we did in the course, guys. Let me show you what it is. Remember this equation? Right. What you have in the left-hand side of this equation is the same as this, right? This and this are the same as the left-hand side, all right? Therefore, what you have is a chi-squared variable with n minus 1 degree of freedom by equation 72 greater than and plus the probability that a chi-squared with n minus 1 is less than all right. You can see here that from this line to this line, I have get rid of the conditioning because the conditioning has been used to say that these two have the chi-square distribution, and therefore we have used the condition, so we don't need the conditioning anymore, right? Okay. So over here, so this, I mean, you can leave it like this, you get full mark, but if you like, you can simplify, well, not simplify really, you can just write it in a neater form. You can write this as the first probability as 1 minus the probability that and finally, if you like, you can write this as the f. This notation here means that this is the CDF. Capital F usually stands for the CDF, as you know. So this means that the CDF of the chi-square distribution with n minus 1 degree of freedom at all right, so that completes. So this is the power function for part 1 of the question. I had it here, see this one. And the two remaining parts are similar, so I will not do them, right? So this is for part 1, part 2, part 3 are similar, right? All right, guys, other questions? Yes? Come on, guys. You want me to come around and ask you questions? Yeah. What about you guys have questions? You all ready for the exam? Yeah. What about you? Any other questions, guys, please? All right, guys, I found one question. Let me see which one it is. 2000. Come. Yeah, it's this one, guys. This is question 6 from 2000. Question 6 from 2014-15, right? Right. So let's look at part 1. Yeah. Part 1 is you have the hypothesis that theta equal to k versus theta equal to L, where k is greater than L, right? And you're asked to find the most powerful test, which automatically means that you need to use the NP lemma, right? So the first thing you must say is the following, that by NP lemma, this is small k, okay? This is capital, I know it's kind of confusing, but this is capital K. Isn't all right? So this is the likelihood at capital K, and this is the likelihood at capital L. Yeah? Now, I assume that you know how to simplify this, right? You should simplify this. You get A power n, capital K power NA, then product of xi, I from 1 to n. Yes? And what's the product of this, guys? Let me test your memory now. The product of this will be? Huh? Come on, guys. You should. The product of this is the min of xi greater than capital K. Yeah? Then in the denominator you have the similar stuff. This is the one of the formulas in the formula sheet you need to remember. So you should know by now. I'm sure you know, you guys know this. Okay? All right, now you see a lot of things cancel. you see that this guy here cancels out with this goes with this. So the only thing that remains are these two terms and these two terms, right? Okay. So all right. Okay, now if you look at the left-hand side of this inequality, right, the only term that involves the data are the x's. The only term that involves the data is the min of xi. So it depends, it's a function of the data through min of xi. So you can call this, say, a function g. I mean, g is any notation, all right, g of min of xi less than k, right? Okay. Now the next thing to do is to let me put this over here. The next thing to do is to try and plot g and see how it looks like. So I'm going to plot over here. On the x-axis you have the min of xi, and y-axis you have g of the minimum of xi. Okay. And let's take the 2 points where suppose this is k and suppose this is L, right? And we are told that k is greater than L, so it should be like this, right? Now the next thing to do is the easy way to plot this is to take 3 points, 1 point here, a point here, and a point here, and check what value the function takes at these 3 points. So let's start with this one, right? Over here, what would this be equal to, guys? The min of this will be equal to, and this one is also 0, right? So 0 divided by 0 is undefined, right? So basically the function is undefined here, right? Okay, the function is undefined when you are less than L. Right now, you should take this point that is between L and K, right? This will be equal to 0, right? And this will be equal to 1. Yeah? So 0 divided by 1 is 0. So the function will be equal to 0. It's equal to 0 between these 2 points, right? Now, let's take this point here. Yeah, here you are greater than k, so this is 1, this is also 1, right? 1 divided is 1, so it will be equal to this point here, which is equal to k power na divided by L power na. All right. So basically, you have a stepwise. So the function we have drawn is not a continuous function, but it's a stepwise increasing function, right? Yeah. It's a stepwise increasing function. So now let's go back to this guy here. G is equal to min of xi less than k. Now, to simplify this, I'm going to take inverse both sides. So I'm going to take all right. Now I know for this function the inverse is strictly not defined, but just for the sake of argument, suppose it is defined. All right. I know in statistics we don't really follow mathematics as strictly as mathematicians do, right? You know, sometimes we take things. Okay, right. I know the mathematician would not do that because he checks all the convergence and the rate of convergence and so on. But in statistics, we don't always check those things, you know, right? So you should take the inverse functions both sides, right? Assuming that the inverse function exists, right? The less than will remain the less than, right? Because e is a stepwise increasing function, right? So this will become the min of xi is less than g inverse of k, and I call this. You can call this whatever name you say c. So by the NP lemma, so the conclusion for part 1 is that by NP lemma, we reject H0 if the minimum of xi is less than a constant c. And of course, you need to determine the value for c. That's the next part of the question. I hope you can do this by yourself, I guess. This is where you need to determine the value for c. And I assume you can do it by yourself. Yeah, okay. Now, before, I know formally this is the last lecture, but I will hopefully see you guys tomorrow also, to the 2 example classes tomorrow. And now, before you go, I'd like to say a couple of things. One, I really like teaching this course because I've been teaching this for 10 years, as I said before, and I hope to continue teaching this course for second year students. But there's also one other course I teach, which is a third year course. It's called Math. Three eight four eight one. 38. I'm not sure the number. I forgot the number already. Come on. I can't remember the number. Anyway, I think it's 38381 or something. Maybe 48381, something like this. You can look it up in the school website. Anyway, the course is called Extreme Values. It's called Extreme Values and Financial Risk. I've been running this course for the last 3 or 4 years, and it's been a really popular course. Among the third year students. But unfortunately, there is a class limit on the course. So there is a cap. There's a limit on the number of students that can take this course. So if you would like to take the course, you need to register as soon as you can. Yeah. And as I said, this has been a very, very popular course. And last year, it got the best rating in the school for all the courses. And it's the best student rating for all the courses in the school. And if you want to know more details about this course, you can go to my website, which is, I'm sure all of you know my website, right? So anyway, I will write it down. All right, this is This is the course website for the third year level. And if you like to take the fourth year level, the difference between these two is that this is 10 credit, this is 15 credit, right? So you can choose one of either the 10 credit version or the 15 credit version. So this is for the third year version. For the fourth year version, it is extremes. Yeah. So this is the fourth year version, right? I really hope that you guys take this course, and I really like to see you guys again, because I don't want to miss you guys, because it's been a pleasure teaching you guys this semester, right? Yeah, and I really hope you can see all the material for this course in this website. There are tons of material online. I hope you like it. Okay? All right, thank you. Thank you, guys. All right, and thank you once again. You received my email about the office hours for the final exam, right? And I'll be in my office until the 23rd of May. And any questions you have, just drop in and see me. And you can also email me 24/7, even early in the morning, all right? Including, you can email me too, all right? So I'll be happy to answer all your questions. All right, so good luck once again, all right? Okay. Just an